for the first part of this problem from 2015, we are going to sketch a slope field. And we only need to do the 6 points indicated, so we don't have to do 0, 0, or 1, 0, even though we could. We don't have to. So it doesn't matter where we start. If I start on the y-axis, so if I start with 0, 2, and remember, we need to evaluate the derivative at each point. So 0, 2, if it's 2x plus y, that's 0 minus 2. So we have a slope of negative 2. So now at that point, we need to draw a little line segment with a slope of negative 2, and these are approximate. We need to do this for each point. So dy dx at the point 0, 1. 2 times 0, so 0 minus 1, I get a slope of negative 1. So we draw that slope. We skip 0, 0, there's no point there. If I go down to 0, negative 1, I have 0 minus negative 1, so now I have a slope of positive 1 down here. And we need to do the same thing for the 3 other points. So dy dx at 1, 2. 2 times 1 minus y, oh, that's just 0. Need to do 1, 1. 2 times 1 minus y is 1. And then we need to do 1, negative 1. Usually when you have a problem like this, they'll only ask you to do a few points. You don't have to do an entire big field like we saw with the first problem. What is it am I doing? 2 times 1 minus negative 1. So that's a slope of 3. So that should be steeper. And that's it. Now we're looking for the second derivative in terms of x and y. So if dy dx is 2x minus y, and I'm taking its derivative. The derivative of 2x is just 2. The derivative of y is dy dx. And this is from, I think, chapter 3, section 5, with implicit differentiation is what we're doing there. So remember, every time x's and y's are mixed and we're taking the derivative, if we take the derivative of y, then we need to have a dy dx. And what we want, so we want the derivative in terms of x and y. That dy dx is a problem. But we know what dy dx is. dy dx is 2x minus y. So I'm going to get 2 minus 2x plus y is my answer for the second derivative. And they want us to talk about the concavity. So concavity, we're looking at second derivative. Oops. Anytime it's positive, we know that it's concave up, and anytime the second derivative is negative, we know it's concave down. So there has to be something related to that. And quadrant 2. So we have a second derivative of 2 minus 2x plus y, and in quadrant 2, we know what? We know that x is less than 0, and we know that y is greater than 0. So if x is negative and y is positive, then 2 minus 2x plus y would be positive, because it would end up being like 2 minus a negative number plus a positive number. So that's always going to be positive no matter what. So we want to say something that we know that the second derivative is positive. So all solution curves in quadrant 2 are concave up. Okay, so we have a point, 2, 3. Sorry, Okay, that was an alert that it is going to rain. Nice. Okay, so we have this point 2 comma 3. Is it a min, max, or neither? So what I would do is a quick test. Is the derivative positive, negative, or is the derivative 0 at this point? We can do like a quick little check. If I plug 2 comma 3, 4 minus 3, I get 1. So what's significant about that, there's a couple of things. First of all, it's positive, which means the graph is increasing. And second, it's not 0, which means we cannot have a minimum or a maximum here. To have a min or a max, the derivative must be 0. So if it were a minimum or a maximum, the derivative equals 0. But since the derivative at this point 2 comma 3 is 1, the curve doesn't have a min or a maximum. Part D of this question definitely requires some creativity, because we have dy dx is 2x minus y, and we're told y equals mx plus b is a solution. What the solution means antiderivative. So we're told that this is the antiderivative, but we're looking for the values of m and b. And what we need to, the reason why this problem is a little bit harder is this is not something we can solve by separating the variables. Even though I can move the y over to the other side, like if I make it y plus dy dx equals 2x, so I can move the y over to the left, but I cannot move the dx over to the right side. Because if I multiplied everything by dx to try to clear the fraction, I would have a y dx plus dy equals 2x dx. So the derivative, the x's and y's, it's not a separable equation. That means that we cannot find the antiderivative. That means that we need to work with the derivative only. So we cannot separate the x's and y's. The main problem with not being able to separate the x's and y's is that it was 2x minus y. So the big problem is that we had subtraction up there. And that means we're going to need another row. So if we cannot find the antiderivative, we have to be able to use what we have. We have to be able to use the derivative. So I know dy dx is 2x minus y. Over here, we know that y is mx plus b. That tells us that for this, dy dx is just m. The derivative of mx plus b is m. So if we know dy dx equals m, we know that m equals 2x minus y. Just a little substitution there. So we know that m is 2x minus y. We're still a little bit stuck here because now I kind of have three variables. I have m, I have x, and I have y. Not particularly helpful, but we can get rid of one of these. We can get rid of the y, making another substitution. So we know over here, we know y equals mx plus b. So let's substitute that in. So we would have m equals 2x minus mx minus b. So we have 0 equals 2x minus mx minus b minus m. So we have two things here. We have x's. We have 2x minus mx, and that is a variable. We have our x. And then we have b and we have m, and those are our constants. I might look at it kind of like this. So The key here is that this has to be a true statement for all x. So it doesn't matter what x I plug in, this has to be a true statement. If 2 minus m times x minus b plus m, if this whole thing has to be true for all x and this whole thing is equal to 0, so that's important. So this whole thing over here on the right, this whole thing is equal to 0 no matter what I plug in for x. What that means is that each of these has to equal 0 itself. I know that's a little confusing, but the only way that we're going to be able to have something times x equals 0, no matter what I plug in for x, that something has to be 0. That gives us our m value. It gives us that m is 2. If we know that m is 2, and we know that b plus m also has to equal 0, it gives us b equals -2. So I know that that is a little bit strange. This whole question was worth 3 points. It was worth 1 point to get dy dx equals m, and it was 1 point to make this substitution over here, and then the final answer was worth the 3rd point. So I know that it's this step in here that feels a little bit like funny math, but the emphasis, the importance of this being true for all x is what matters here. So the only way for that statement to equal 0 for all x no matter what is if everything was equal to 0. That's the only way for that to happen. So that is the breakdown for this question. If you have any problems, if anything is still confusing, please reach out and let me know.